Hi, everyone. I'm Junchen. I'm a CS professor at U Chicago. I lead the LLM Cache Lab. And joining with me today is Yue from IBM Research, a close collaborator.
Thanks, Junchen, for the short introductions. I'm Yue from the IBM Research and collaborating with Junchen on the LLM cache work. And just want to mention that for today's presentation, it does not represent any IBM's views on this project. Thank you.
All right, excited. First of all, with our decade-long research in large-scale AI systems, I want to share with you today what we believe will be the future of AI infra. In particular, we believe that large language model or LLM inference will be the dominating workload in the future, in the near future actually. And LLM inference can be much cheaper and faster, and everyone can own such a system by themselves with one click. Okay, and that's the future. And how do we get there? First of all, why inference? Right? Why LLM inference, not training? Now, generally, everyone knows an LLM system has two parts: the training part, the inference part. For training, I mean, trillions of dollars has been spent on training these days. Of course, it's important, but only a handful of companies are going to be focusing on training new models. What's more important is millions of applications or organizations will be running inference, will be running these large language models for their users, which is inference. Okay? And this number will only grow because more users want to use large language models, and more use cases will be discovered in the future. By one estimate, for example, Microsoft says there are going to be 750 million applications using large language models next year. And many industry leaders believe that every single applications will be running large language models in the backend. So in other words, inference rather than training will be the dominating workload in the future, will be the biggest opportunity for system development or research in the coming years. Now, the problem is, LLM inference is extremely challenging. It poses the biggest challenge in the history of system research, probably. Okay? First of all, LLM inference is expensive. Okay? Training is a one-time cost. It's expensive, of course, but it's a one-time cost. In the future, I mean, after the model is trained, every single query incurs a cost. In fact, every single token incurs a cost. And that cost will grow with the length of the input and output. And second, inference is not just expensive, it's slow. Okay? Every input-output token will increase the inference delay. And to make it worse, people tend to make the input long, so-called long context inference. And people tend to make the output long, so-called long decoding reasoning. Okay? So that's the problem. And a lot of people these days believe that the inference engine itself, that single piece of inference engine like SGLang or vLLM is good enough. They're not good enough. There's still huge room for improvement on top of what vLLM or SGLang inference engines can do. And third, it's not just expensive, it's slow. The model itself is a moving target. Okay? Every week, there's a new model. There's a new open source model pushing the boundary of the quality of open source large language models. And if you're a good engineer, you want to build a system to serve that model. Okay? But serving that model efficiently, that new model efficiently requires potentially new optimizations. And that's the pain in the ass for every engineer. And finally, for open source community, we are here because we want to build open source project. We want to self-host these services, right? Now, there are a lot of open source projects. I'm not going to name them, but there are a lot of open source projects out there. They're extremely painful to deploy. We have a bunch of very fantastic students, and every time a new open source project comes out, it took them at least 5 days to manage to run them in their probably alpha version. So self-hosting these open source projects to serve large language model at scale is also painful. So just in short, 4 problems. Inference is slow, inference is expensive, inference is hard to catch new open source models, and self-hosting these open source systems is painful. What's the solution here? Okay? A solution is the missing piece in the AI stack. People think AI stack is application, and then model, and then hardware. But there's a huge missing piece in the middle called inference stack. The inference stack is a new beast in the world these days. There are a lot of offering the open source projects, but ultimately, they need to be what? They need to have low inference delay. They need to be cheap. They need to have low cost. They need to support latest models effortlessly. And finally, more importantly, you need to be able to self-host this stack effortlessly as well. So how do we do that? Good news is, in research, in industry, there are a lot of pieces of solutions here and there. Okay, I'm going to just list some of the things here, and each box here solves a subset of these problems on the right. Okay, but now I'm going to say why don't we put them together? The problem is putting them together is extremely large. I mean, it's a huge effort. Okay. Now, good news is we do have a solution for that. We built open source projects together with collaborators, and these these pieces are part of this solution, and I know this is a lot to read. I'm going to highlight some of these pieces in the later slides. But in a nutshell, these three pieces: the production stack project, which is sitting on top of everything, it's a high-performance distribution layer for vLLM serving engines, and then below that is the vLLM serving engine, which supports the latest LLM and the latest hardware, driven by its large community. And finally, the LLM cache layer, the one that really is the secret sauce of performance optimization. Now, only these three things are not good enough because, well, these are just yet another open source project. The problem, and the good news is we also have a one-click no-code deployment layer, a packaging of these projects. So for people who don't want to deploy open source projects and just want to use UI, that would be good for them. And also, it runs on top of any cloud because it can use SkyPilot to create new GPU instances here and there in any GPU cloud of your choice. Together, we call it LLM Cache Cloud. The project, if you combine all these 5 things together, we call it LLM Cache Cloud. And the critical pieces of this stack are all open source. Okay, you can scan the QR code. The QR code will be there in the later slides. Don't worry. Okay, but they are open source. You can find them. The production stack is under vLLM project space. LLM Cache is in a different organization. Now, it sounds good, right? But Junchen, you did talk about performance. Where's the performance? So the real reason we think everyone should use LLM Cache Cloud is because of its superior performance. Okay, LLM Cache Cloud in itself is an open source project, but it's not the only open source project. Now we can compare performance. Open source projects in this figure, for example, in this particular workload, we can put these open source project and closed source API services on this performance trade-off, which, I mean, not really trade-off, but 2 dimensions. On the x-axis is time to first token, faster the better, lower the better. And y-axis is the time per output token. Again, smaller the better. And you can see, compared to different open source projects and other closed source systems, LLM Cache Cloud is much better in this long context query. Not just long context query, you can think about other typical workload like multi-round chat applications, and finally, batch offline inference. Across all these workloads, LLM Cache Cloud is much better than other things. Now, superior performance is definitely the key why people are using LLM Cache library these days. Now, but why LLM Cache Cloud can have such a good performance? The key lies in a lot of the research project we did in and around the space of KV cache. So what is KV cache? KV cache, I believe a lot of people in the space of large language model system are aware of what KV cache is. But in a nutshell, KV cache is the internal representation, 2 tensors, a pair of tensors that represent models' understanding of a sequence of tokens. Okay? So our goal is to proactively manage and reuse KV cache. Now, why KV cache after all, right? KV cache, like I said, is just another representation of tokens of information specific to large language models, specific to a particular large language model, to be specific. Now, KV cache is definitely not the only representation of information, right? Tokens can be representation of information. The model weight itself can be representation of information. But why KV cache? Well, the KV cache is unique in the sense that it caches models' understanding of any new tokens. Okay? Doesn't have to be part of training data. Training data is captured in the model weights. KV cache captures information in the new tokens, the token it has never seen before. So as long as there are new information for a model to take, KV cache is the right representation for information. Now we argue that basically in large language model inference, feeding information across across things using KV cache is the right approach. Okay, and because KV cache captures large language models' internal understanding of context. So enough about high-level abstract things. Let's talk about architecture, how these KV cache optimizations reflect in the architecture. So like I said, the architecture has 3 parts. The production stack part, which is an open source project to scale the inference of across multiple vLLM serving engine instances. And vLLM is the layer below that. And finally is the LLM cache project. The LLM cache project is the KV cache backend. The KV cache backend that stores and manages and transforms and share KV caches across vLLM instances efficiently, quickly, and effortlessly. Okay, so the key primitive supported by the system is very simple, 2 things, store and load. Now, store KV cache means when a new query comes in, the model hasn't seen this query's context or input-output before, the model has to read the input, for example, okay? And in the process of reading the input, it creates the KV cache of those input tokens. And when the KV cache is created, potentially that input maybe a book, maybe an article, maybe a music, maybe a song, maybe a picture or video, but if that input will be reused in the future, okay? And that KV cache needs to be stored. And the storing of KV cache doesn't just rely on GPU memory. Okay? Most of the serving engines these days only keep KV cache in GPU memory. It's very ephemeral. It's very short term. What we want is a long-term storage of KV cache that can reuse KV cache permanently. Okay? So the KV cache will be stored in the backend. In the future, if a query comes in, this new query needs the same context. Let's say it's a different query of the same book, of the same article, of the same music that the model have seen before. The KV cache can be loaded back to the GPU memory in a way that the model can skip a lot of computation, and it reduces cost. It reduces the prefill delay, so-called. Okay. Now, this all sounds good, right? But it's just functionally, it's just store and load. The devil's in the detail. How do you really optimize the performance of such a system? We have seen probably, I mean, this is actually not new. A lot of open source projects claim they store KV cache here and there, but if you run the system, sometimes storing KV cache makes the system even slower than not storing them, okay? So we don't have that problem because of a lot of optimizations. For example, we have the kernel optimized store and load library in the LLM cache project. So loading KV cache from the CPU memory or disk into GPU memory can be much, much faster than, say, if you do this with PyTorch Safe. Not just loading KV cache between CPU and GPU, the loading of KV cache sometimes also need to go through the network. And the network has much lower bandwidth than the GPU I/O. Now, to deal with the bandwidth limitation, what we did is we have research to, I mean, actually not us, a lot of papers these days are talking about compressing KV cache, possibly in a very carefully lossy way, to compress KV cache so the KV cache can be shared across instances in an efficient, I mean, very, very fast without compromising quality. And LLM cache library supports that. Now, not just loading one particular piece of KV cache, just reusing the same KV cache all the time. You can concatenate KV cache in a smart way. So, for example, if you the model has read article A, and then the model has read an article B. Now the model has created the KV cache of article A and article B separately. Now, if a user wants to ask a question that involves information from article A and B, right? The model needs to read those 2 articles. How do you combine the KV cache of these 2 articles together? Now, we have some papers to do that. And again, this is not a research conference. This is open source summit, so I'm not going to go into detail. The idea here is combining KV cache in itself requires careful editing of the KV cache content to preserve cross-attention. And again, that's a research paper. I'm not going to bother you. The whole thing is this will be a very handy tool to improve performance of RAG systems, for example, because RAG, you have to combine multiple tokens together, I mean, multiple chunks together, okay? Now, this is about the LLM cache library. Now, beyond the LLM cache library, the production stack, the router sitting on top of all these multiple vLLM serving engines also needs to be smart, right? This is, now, you probably have seen people saying, well, you can do session-based routing, so all the query of the same user will be routed to the same vLLM engine, and that the engine will have the KV cache locally, blah, blah, blah. That's actually true, but in reality, the workload is not going to be that evenly distributed. Some users are going to have a lot of queries, a lot more queries than others. And if you have a lot more queries than others, the KV cache cannot be saved on one node because that node is going to be a hotspot. You want to distribute KV cache across nodes. Now, once the KV cache is distributed across nodes, the router is not going to be, so the router, it's not enough for the router just to be aware who issued the query. It also needs to be aware where the KV cache is in the system and route request in a KV cache aware way. So that's something the router needs to be smart about. And finally, I'm just browsing some, it's a little bit laundry list, forgive me about that, but these are just key optimizations. The last thing I want to mention is this Nixle-based KV cache transfer, and this is used for something called PD disaggregation, not DP, PD disaggregation, pre-field decoding disaggregation. And that is, I mean, Yue is the expert on that. I'm going to leave Yue to say a few words.
So it's for the PD disaggregations that we want to to pull the KV cache from the prefillings to the decoding phases. That, as we all know, that on this slides, it shows that the prefilling phase, as everyone knows, is more computation intensive, and for the decoding phase, is more memory intensive. But for these two different phases, they scales differently. So co-locating them on the same node may waste the GPU, CPU, and memory efficiencies if we want to scale out. And for the traditional network, it may not allow the direct GPU to GPU communications on the Kubernetes cluster. So that's why we say we probably need to enable the RDMA for the disaggregated PD to make the prefilling and decoding more efficient. So on the next slide, I'm going to show is for the GPU direct RDMA support for the disaggregated PD. So it's basically the decoding pod can directly push KV cache from the prefilling pods with the Nixle support, and this allows the zero copy data transfer across the nodes and also the CPU bypassing. So for here, it's just a two examples that we're trying to demonstrate that how we can enable the GDR with the Nixle, and this example is done on the Melter CNI. So here, the annotation we are showing here is just to allow the pods for the prefilling and the decoding pods to use the secondary network. And this secondary network can give you the high-speed network access. And the security context here is to grant the privilege to the prefilling and decoding pods. So the pods can have the direct access to the high-speed network and can bypass the regular default Kubernetes interconnects between the nodes. And so the resource here is just to request, this is the RDMA resource we want to require for the prefilling codes and the decoding code, decoding pods and the prefilling pods. And the last two environment variable is the most important environment variable for the UCX, which is used as the underlayer library for the Nixle. And here is to enable the data transfer protocol for the GPU direct RDMA. And so for this demo, we are going to show how we deploy the prefilling pod and the decoding pod on the two separate nodes and using the GPU direct RDMA as the data transfer between the nodes. And for the demo setup, we are using the Llama 3.18 billion models. And also for the benchmarking, we are going to show we are using the vLLMs benchmark serving scripts. And as we're showing here, we are using the random data sets and have the input-output length, number of prompts, and the request rate showing on the slides. So let's move to the most exciting part about the demo. So on the screen, we are showing that we have two, this is two example. We have two RDMA nodes set up. And for both of the two nodes, we do have the RDMA resources that we mentioned on the previous slides that can be assigned to the prefilling and the decoding part. And so let me move it a bit upper. So on the next step, what we are going to show is some customized changes we made to the YAML files for deploying the Helm chart. So for here, this is the disaggregated prefilling and the decoding deployments YAML file from the production stack. Production stacks tutorial. So basically, we set up the RDMA node 1 for the node selector, and also for the LLM cache configurations, we set up the secondary network for the RDMA direct RDMA transfer, and also the UCX environment variables. So what we just shown is for the prefilling code, and what we are going to show is for the decoding part. The similar things we are asking. Put the pod on the RDMA node 2, asking for the RDMA resources, set up the secondary network, the UCX environment variable values for the decoding pods. And so on the next step, what we are going to show is about the deployment YAML files that we generated through the project. So basically for here, it's showing like the pod annotations for using the secondary network. And also, if it comes a little bit further, we're going to show that we have set up the security context to have the privileged pod and also use the IPC lock. And this is to prevent the UCX and the memory used by the UCX to be swapped out. And so for here is the UCX environment variable value we set up to use for the data transfer protocol. And at the later phase, we are going to show is the RDMA resources we are asked for this prefilling part. And if we go a bit further, this is just to see we put the prefilling pod on the RDMA node 1. And then we are going to show the similar things for the decoding parts. So the similar things here is for the secondary network annotation, security context, the UCX environment variable setups, and also at the later phase is for the node selector to put the prefilling phase on our second RDMA node. And this is to showing that we have the RDMA resources asked for the prefilling part, and this is for the RDMA node. So here what we are going to show is for the deployments, and we use the Helm chart to deploy the disaggregated PD for the GPU direct RDMA. And once the pod is in the ready state, we forward the service so we can send the request locally. So for the performance benchmarking we are showing here is just to give you some sense of how the performance is going to be look like. We are using the vLLMs benchmarking scripts, and so here we are showing is the performance parameter, the input parameters that we put in for this performance for showing the performance, and we speed up the video here just because of the time concern. But you see, gonna be super quick. For the time, for the results, we are going to show is for the time to first token, and we can see that for the time to first token, which is a very good performance number. But we are also going to show a bad example about how if the UCX was not set up correctly. So in this is in a different deployments and still the same things. The only thing we are going to show here is if we are using the TCP for the UCX TLS environment variable. So for here, we change the RC to the TCP for the prefilling pod, and also we can change it to the decoding pods. And since we have already shown this portion, so we try to speed up everything so we can get to the next stage to show the performance numbers that we had for using the TCP for using the TCP transfer protocols for UCX. So for here, we issue the similar commands, and the performance, we can see the progress over here is compared to the previous one is a bit slow. But although we have speed up for like couple of times X, but it's still, if you look at the bottom, since just the same number of requests, it's already took like a few minutes to issue to finish the same number of requests. And then what we are going to show is for still for the time to first token, but comparing to the time first token we just showed with enabling the GPU direct RDMA, we can see a huge differences in terms of the time to first token. So this is just our two example about how we enable, how we can use the GPU direct RDMA with the Nixel library for disaggregated PD. So I'm going to hand over the rest to Junchen.
Okay, great. Just so you know, you probably don't remember the numbers before. This was, this is about 8-ish seconds. The one before was 1.4 seconds. Okay, so a large difference. Okay, so thanks, Yue. So this is a very good demo to give you a direct sense how much better the performance could be. By the way, the only thing changed here is just how you do GPU to GPU communication for PD disaggregation. That's the only thing changed. Everything else didn't change, okay? It's the same vLLM serving engine, same version, same workload. Everything else is the same, except that optimization of the GPU to GPU communication, and that makes a huge difference in the PD disaggregation performance. Now, so far, all we have seen is LLM Cache Cloud, it is LLM Cache Library, Production Stack, vLLM. When combined, offers the best performance. But we want to make sure that everyone can use it easily. Okay? Everyone can use it easily, not just super experienced backend engineers. We want every user to use it easily too. So that's why we have been building this one-click, no-code deployment. It's basically a web interface that you can self-host, and the web interface will give you the same experience as, say, Together AI or Fireworks AI. It's the same as that. You can specify the number of GPUs, where the GPUs are from, and then just click one click. It creates a cluster for you. Now, that's just a cluster, and then there's another click. Okay, two clicks. Then the other click give you, let you choose which model to use, and then directly deploy the model in that cluster. Okay, so 2 clicks, not 1 click, but very effortlessly, because the point here is we want to give people the same experience, same smooth experience as those APIs, but you can self-host this fantastic software stack in the GPU cloud of your choice. Now, that's just a user interface. How do we deploy this in any cloud, GPU cloud? We just shamelessly use SkyPilot. There's a wonderful project from Berkeley that lets you create instances, including GPU instances from any GPU cloud, or actually any cloud of your choice, like GCP or Lambda. And once SkyPilot creates these raw instances, then our software will create a Kubernetes environment, create a router, create a vLLM instance running instance environment, create the KV cache backend for you. Okay, and this created Kubernetes environment will have all these Kubernetes native management, auto scaling, and also a very nice looking Grafana-based performance dashboard. I don't have the time to show that now, but yeah, you know what it looks like. The other thing I want to highlight is this compatibility with upstream vLLM serving engine. This, many people feel like, well, vLLM serving engine is just a project. It's out there. We can just check out a version, run it in my backend. A lot of people have done it, and a lot of people fail, well, miserably. The reason is because vLLM serving engine itself is a really, really fast-moving project. The reason it's fast-moving is because there's so many new new models to adapt to. Okay, and you need to, and also new hardware. So anytime, for example, NVIDIA has a new GPU, you need a special kernel optimizations for vLLM to run on that GPU. Otherwise, it's a waste of money, because you cannot get the best performance from that GPU. vLLM does that for you. So again, vLLM, tremendous credit for vLLM team. But one thing we did very well is we have direct compatibility with the vLLM serving engine. Everything else will be compatible with the upstream vLLM serving engine. Okay, so let me just summarize what I'm really talking about in this two-dimensional graph. On the x-axis, we want the best performance from this system. On the y-axis, we want the best user experience from such an LLM serving system. Now, where are we these days? Well, there are open source projects with good performance, sort of okay performance, I would say. But user experience is well, let's be honest, open source projects, especially at that scale, is hard to use. Then there's also the cloud-based API, together AI, Fireworks, Base 10. There are a lot of projects and deep infra. There are a lot of commercial API services that have very good user experience because they charge people for that. But the point is, their performance is not actually better than a lot of open source projects these days. We benchmark it, for example, Fireworks has the same, almost same performance as raw vLLM. It's the same thing. Now, what we have been doing is first, we want to push the boundary of performance. Apply some research ideas from the research community, the ML system research community, to push the performance to a better, the better level first. And that's why we have a lot of users these days of this open source project. But again, I'll be very honest with you. These companies all complain our open source projects is hard to use. So we're not improving on the y-axis. What we're doing today is to show you, to give you this this preview of what we are building now. A one-click, two-click deployment of this open source project called LLM Cache Cloud, so people can use it easily. Okay, it's the same performance and people can use it easily. The same interface as Together and Fireworks, best serving engine, best research ideas. Now, I want to summarize. It's a solution. It's a 10x solution. It's a combination of open source project like vLLM, the vLLM production stack project, and LLM cache, and wrapped with this one-click deployment. And in it, there are two key sources. One is the LLM Cache project, an open source project that manages KV cache, including compression, blending, translations, and KV cache sharing, and so forth. And there's the other projects called vLLM Production Stack. It's easy to, so it's not so easy, but it's a good deployment stack of vLLM engines. It's cloud native, it's fault tolerance, it is auto scaling, it's open source. Okay. If you want to contact us, there's the email. And very happy to share this with you, and I'm happy to take any questions. We're happy to take any questions. Thank you. So just raise your hand, or you can just shout. Okay, so the auto-scaling part, right? So the auto-scaling part right now in vLLM, in the vLLM production stack is, so basically when you launch SkyPilot nodes, right? The SkyPilot nodes, I mean, it's just a one-click deployment. You can just command line increase, I mean, add a new node to the Kubernetes cluster that's already been created. So mechanically, it's based on SkyPilot. Now, the logic behind when to autoscale, when to increase and decrease, that's a very interesting question. Right now, the logic is very simple. We want people to be able to write the logic for themselves. Right now, the logic is simply if the load of these nodes are over some threshold, like the load is defined by number of jobs the number of jobs in vLLM serving engine, in the queue of a vLLM serving engine. If that exceeds the threshold, you create a new node. If that's lower than a threshold for a period of time, then you create a new. You can just turn off some of the nodes. Make sense? Yeah. So that's we don't want to dictate these algorithms. Algorithms should be developer's choice. Model cache, the cache of the LLM model weights, right? Oh, these model. So what's the question again? Okay. Yeah, I mean, it's a good question. So how do we handle model cache? Now, first of all, model cache, if you cache the model somewhere very close to the eventual GPU, so at the GPU node, it's a very good thing. I mean, it's a very good idea to reduce the startup delay, because the startup delay involves launching a vLLM serving engine, creating the clusters, launching the serving engine, and load the model weights. Typically, loading the model weights, to be honest, it's not the biggest overhead. I mean, it's painful, especially if the model is loaded from somewhere you don't have good connection to. So loading, I think we don't have the optimization for that, to be honest. The real pain when deploying a system like this is vRM itself actually take a long time to launch. And that's something we have spent a lot of time to optimize, such as, okay, I have to check with the developers, but their configurations, their arguments to turn on and turn off to make vRM launch faster and faster. And also we can parallelize the launch of the ARM cache, the ARM cache backend and vRM together. The reason is, when you launch vRM, it sort of formats, profiles the GPU memory. ARM cache also formats the CPU memory and disk, sort of prepare that for the KV cache backend. And these two things are actually the bulk of the delay of startup. So again, I'm not answering your question directly, but the loading model is important, but right now it's not the main bottleneck yet. Yes.
Now, are there any situations where we lose performance using LLM cache or any trade-offs?
Totally, any system has trade-offs. Now, but the thing is how big is the trade-off, right? So right now, ARM cache has to. Okay, without ARM cache, if you have a KV cache in GPU memory and GPU memory doesn't have enough space for all the new KV cache and to kick out some KV cache. Right now, without ARM cache, vRM will just delete it. But with with ARM cache, you have to sort of store the KV cache that's offloaded from the GPU memory. So that offloading is overhead. It's extra overhead. Right? It's storing extra overloaded KV cache from GPU memory to CPU memory is overhead. Okay? Now, that's an extra overhead because of ARM cache, but that overhead can be minimized. The overhead, as long as the loading and storing and retrieving of KV cache between CPU and GPU is asynchronous, it's done asynchronously with the vRM serving, the serving process, then users will see very minimal increase of inference delay. Our latest benchmark was that increase will be about 3 to 5%.
The LLM cache actually stored in the system RAM at that point in time, and if so, do you need a one-for-one of the system RAM to VRAM?
Sorry, what's the last part again?
It is stored in the system.
Uh-huh.
You need a one-for-one of the VRAM compared to system RAM?
You mean the CPU RAM has to reserve? The size of the CPU RAM has to reserve as big as GPU memory. Is that a question? Yeah. Okay. So that's not a strong restriction, right? So you can have any size GPU, reserve CPU memory of any size. If you reserve more CPU memory, you keep more KV cache. Now, of course, it's not just CPU memory. KV cache will store in multiple layers. CPU memory is the layer right below GPU memory. If CPU is not enough, you're going to offload that to disk. So it's a typical hierarchical caching system. So the size of each layer is not it's a parameter, important parameter, but most importantly, it's the workload, the locality of the workload that dictate the performance of the system. Yes.
For long-running instances, do you need to be worried about
Pruning.
keys that are commonly used to preserve cache space? Is that something you guys are
Oh, that's a good idea. So let me try to rephrase. So I think sometimes if the KV cache is too big, there are too many KV caches in the system. Maybe instead of just deleting some of them, you can compress it, right? You can prune the KV cache, maybe dropping some tokens in the KV cache. That's an idea. Actually, a lot of papers are doing that. Right now, ARM cache doesn't do that yet. Well, actually, the student sitting there, he's just left. He's actually developing a technique to combine multiple research ideas to prune KV cache in an online fashion with minimal impact to the quality of the KV cache. So that's an idea, but it's more researchy than the open source project right now. Thank you. Anything else? Okay. Oh yeah. So there are.
We just forgot that we put them all downstairs in the baggage shack. We're just fetching them right now. So if you want a shirt like this, it's coming in like 5 minutes.
Yeah, it's a Halloween scene LLM cache. Sure. Please feel free. It's free. Okay. Thank you.